Okay, let's summarize what we have done so far in this semester. So the big parts of this calculus is two parts. So one is differentiation, and the other is integration. So we talked about the differentiation of multivariable functions, and we say that it's given as a matrix. So when you have a multivariable function from n variable to m variable, we simply call this as a n to m function. And we can say that this function has coordinates given as, let's say, f1, f2, and fm. And each of fi is taking n variables, and the value is just real number because it's coordinates of m-dimensional points. And if we want to find out the derivative of a function, this function, multivariable function, at the point P, so when P is a point in Rn, which is the domain of F, then we say that it's a matrix. It's n column and with m rows, and the entries of these matrix is given as the partial derivative of these coordinate functions. So first, we take the partial derivative of first coordinate function with the first variable, and on the same row we have same coordinate function, but with the different columns we have partial derivative with different variables, and so on. We have fm, x1, fm, xn. So this was our definition of derivative. So the concepts of derivation and the integration is, in the single variable case, was kind of reversing the process, but in the multivariable case, it's totally different situation. So we're not in the integration of derivative of multivariable function. We're not going to take an integration of this kind of matrix. So when we talk about, before we talk about the integration, just summarize what we have learned from this differentiation is that this matrix gives a map from a movement in the domain space to the movement in the target space, which means that if you have a domain space Rn and target space Rm, so I made it as a somehow two-dimensional space, but you can say it's a n-dimensional, m-dimensional space. So we have point P that we are interested in, and also there is a Fp which corresponds to the point P in the image. And let's say I have a movement of a point P, and these points are somehow translated in the image, and there is an instant velocity of that movement, and I will call it v. And since we are moving in Rn space, this vector, now it's a movement, so it's a vector. It corresponds to the movement in the image space, and I will call it W. And the differential given as a matrix is a map which maps the V to the W. So that's exactly what I just said. It translates the movement of the point in the domain space to the movement in the target space. So how they are related, so I will just call it, the map is called DPF. And then the formula is that dpf times v is w. So this is multiplication. So dpf, the derivative of function f at point P, is m by n matrix, and v is, as a vector, it's a n-dimensional space. So I can make as a column matrix, as n by 1 matrix, and because it's m by n matrix, I can multiply these two matrices so that I get m by 1 matrix, which corresponds to m-dimensional vector w. So this is the essence, this is the real meaning of differentiation. So by taking derivative of a function, I can say how much of the value of function changes according to the changes in the input variables x. So that's exactly the same what we have learned in the single variable case. We call it, we said that the derivative of single variable function is a slope, or it's instant rate of change. And the slope or rate of change says that how much you change in the x variable determines how much you get in the y variables. So by how you relate those delta x, delta y is by multiplying the derivative of the single variable functions. Here is the same idea we have. Now it's not about quantity, because the movement in n-dimensional space, it's not just the number. It has a speed and velocity represented by vector. So if you want to know how much your image point is moving according to the movement in the image, or you could say that you have n input variables, and let's say I want to change your input. I want to change my input in some directions, or in other words, I want to change my x1 variable this much, and x2 variable that much, and then so on. And I want to see how much the outputs changes according to my changes in x. Then in order to find these output approximately, to find out approximate change of the outputs, I need to know the differential, because that relates to output, the changes in the output. So that was the idea. Okay, so that actually summarizes all material that we have learned before the midterm. And let's talk about the integration. So in the integration, we first started with the function, a real valued function, let's say defined on the two-dimensional space, and we defined integration over a domain in two-dimensional space. And we call it this. So usually we also call this, instead of writing dx dy, we also say dA in some sense. Okay. So basically, we say that this is the volume under the graph of function over domain D. And also you can call it a mass of two-dimensional object whose point density is given by F. And if your function is defined on three-dimensional and value is still a real number, and we can define integration over the volume inside of three-dimensional space. And this is how you denote the triple integral. And also there's a convention notation for these parts. Simply we call it duv. Okay. And again, you can call it, this is a four-dimensional volume who's under the graph of three-variable function f over the volume v, but we have no intuition to that, so simply we related this amount to the mass of the volume v whose point density is f. Okay? So that's when we have a scalar function. You can enlarge this idea to any type of function of this form, which sends n-dimensional points to a real number. And let's say I have a volume or some region inside of Rn space. So A is a set of all n-dimensional points, and there should be some topological definition to say that A is not just a collection of points. It corresponds to some object that I can make an integration on. So maybe I should say it's a closed subset. So this is a topological concept. So I'm not going to define in the detail. But anyway, I can also define the integration of the n-dimensional function, or the function like this one. And now, since I used A in the same symbol for the domain and dA, but you see what I mean. So I'm simply taking integration over this n-dimensional volume. And what I'm doing here is that I chop up all the n-dimensional volume into smaller n-dimensional volume. And for each pieces of small n-dimensional volume, I pick one point and evaluate function at that one point. And I multiply the volume of the small pieces of n-dimensional thing times the value of function, and then add all together to find out the integration. Okay? So once you pass the n bigger than 3, then there's no physical meaning if you're looking at and you cannot look at the shape of A, but in the physics, or if you think about, if you make your problem abstract way, then integration of this kind of function might have meaning. Okay. So that's the integration for scalar function, which means that all these functions have value of real numbers. Okay? And then we move to the case when we have vector field. So vector field is mapping a point to the vectors, and I assume that this vector field has the same dimension for the domain space and the target vector space. But again, I'm saying that for the scalar function there, the Rn and R are both spaces. Okay? But here, for the vector field, the domain is the space, which means that it's a set of points, but the target is the set of vectors, which called the vector space. Okay? There are very different properties. There are very two different things. So point of vector, a set of point, is simply a set of point. We cannot add to point. Okay? If you have this point and that point, there's no way you can add together. But if you're talking about the set of vectors, it's called a vector space, and you can add to vectors. And also you can multiply a scalar to a vector. So there are vector operation on the domain space. And so here, so situation was similar. So when you have a domain D, and if you have a boundary of D, so I'm calling this D as also closed domain, and C is the boundary curve, then you can define a line integration over the curve C. So here, or maybe I start from here. So if you have any not closed curve, but just the open curve like this one, then you can define a line integration along the curve C. And how you define this is going back to the definition of single variable function. So we have f inner product with parametrization of C and which parameterization is the function from interval to a curve C. So I'm taking my parameter from A to B, and the integrand is f inner product with f prime t dt. So basically, we gave this as a meaning of finding a work done by the vector field along the curve C from A to B. Okay, so for when parameter is A to B. So this is when C of A, and this is when C of B. I'm computing how much of this vector field has work done from that point to that. And in this case, since we are talking about the boundary of closed region, this C is also closed curve, so something like this curve. And for that integration, we have a different notation that we have circle O above S and integration. The definition is the same. We simply parameterize our C, and then what we have to do is just using this formula, exactly the same formula. So I'm not going to write this, but Green's theorem tells you that there's another way of obtaining the same results, which is instead of taking line integral, you can take a surface, the double integral of the rotational scalar of this function vector field f. Okay. So that was Green's theorem. And now we move to the vector field of three-dimensional space. So for the three-dimensional space, we can talk about the flux. So let's say we have a surface S inside of R3, and I want to say this is oriented or orientable, which means that I can give an orientation up to this surface. So it's not a Möbius band or Klein bottle, something like that. So in that case, we have defined our flux and denoted by as this. And how we define is the following. So we have parameterization of the surface S as D maps to S. Sorry, so maybe I make it small s here, small s, and large s here. So D is a domain in two-dimensional space. So basically, the surface in the three-dimensional space is parameterized by two parameters. So this D is the space where two parameters lies in. So I'm going to take to find out the flux, we take the double integral over the domain of parameterization, and I take the inner product with F and SU S3 dA. Okay, so there's a we have to be cautious that I only assume that S is orientable, so I have to give an orientation. But in the cross product, it actually determines the orientation because it will going to take SU S3 cross product, which gives this as an orientation. So if you want the opposite orientation, you have to switch your order of cross product. Order depend on the choice of orientation. Okay? So but that's how you get the surface integral, which is called the flux. And if you have a volume inside of R3, it's a closed volume, and you can take the boundary of that volume as the surface S. So it's a closed surface. Then we had a theorem that says that if you take the flux across this closed surface of the vector field, it is equal to the volume integration of divergence of f. Okay. And also, before I have to mention it before it, but if you have a surface S, and if you give an orientation to the boundary of this surface, so I'm assuming that S is not closed in order to have a boundary, then I can also relate the line integration over the line which is the boundary of the surface with the surface integral of the flux. Oh, I'm sorry. So of the curl of the vector field over the surface. Okay. So this is called the Stoke's theorem. Stoke's, and this is called the Divergence Theorem. Okay. So the right-hand side of the Stoke's is computed by the formula here, which is because it's simply we have a vector field given by the curl of f. And we've proved Stoke's theorem in several ways, and you have to understand that the intuitive meaning of the essence or the deep underlying the principle on the Stoke's theorem actually lies on the Green theorem. So Green theorem there. Okay. So that's a summary of what we have learned in this semester. So what we're going to do today is make it more mathematically rigorous. I mean, I'm not going to make concept more rigorous, but mathematically think more rigorously about the conditions and examples and counterexamples of this integration theory. So before we begin, is there any questions on review? So now it's time to ask freely about anything, because it's just for your intellectual curiosity, not because to get any marks or grades for this class. So if you have any questions, ask any time. Okay, so let's think about three types of situations. So I'm going to subdivide this board into three parts. So one of them is that so all three cases assumes that my vector field F is defined on a domain D, which lies in two-dimensional space. Okay, and I'm saying that this F has coordinate function PQ, and these PQ, the S2-variable functions, are differentiable. So I don't worry about taking differentiable. Or taking partial derivative of f and q many times. So first case is when I have for any closed curve C inside of D. So meaning the closed curve means that this curve has started at the starts one point and ends at the same point. Okay, so it always comes back to the original point. It means that, so the condition says that if I take any closed curve inside of the domain of the function, the vector field, then the line integration of this vector field is always 0. Okay, so this is simply a statement. Okay, this is not a theorem. Okay, so this is, you can say this is kind of conditions or properties. So there are some vector fields that satisfy this condition or not. So just this is as a statement. Okay, so statement that you cannot prove whether it's true or not. This is just the argument. And the next one is that or maybe so maybe I can make it into 3-dimensional because I want to make a curl. So let's make it 3-dimensional. So easy to make it 3-dimensional. Just add more coordinates and turn my D into 3-dimensional volume. So this curve C is now a line in a curve in 3-dimensional space. So nothing changed. So, and then the next one is that if I take a curl, this curl of F is 0 vector field. Okay, so that's also a condition. There are some vector field that does satisfy this or does not satisfy these conditions. Okay. And the last one is that there is a function, small f, which maps a point in D to R such that our vector field, the given vector field, is given by the divergence of the scalar function f. So, by the way, since this Nebula is given as the vector of operators, which is del x and del y and del z, and the meaning of taking, maybe I omit this inner product sign, just Nebula f. Meaning is that I take this operator to every f here, or you distribute your f to every operator inside of this vector notation. So basically, it gives fx, fy, fz vectors. Okay. So this last statement says that there is some function, a scalar function defined on 3-dimensional volume, which gives the divergence of that function gives the same vector field f, the f that we defined in the beginning. So I will give a name to all 3 conditions. So this one is that f is a conservative vector field. And the second condition says that its f is a closed vector field. The last condition is that f admits a potential function f. So this f, which satisfies this inequality, is called the potential function, and we call this condition as f admits of potential function f. So let's compare the implications of these three conditions. I think the easiest one is that if f satisfies the second condition, then check whether it satisfies the first, or maybe it satisfies the last conditions. Okay. So maybe I give a number here. So this is 1, this is 2, and this is 3. So let's check whether 2 implies 3. So as I said, this 1, 2, 3 is simply a condition, okay? So I'm not saying I'm not prove whether 1 is true or 2 is true, 3 is true, because there are vector field that satisfies or not satisfies these all three conditions. But what we are going to prove is that the following: for any vector field f satisfying 2 satisfies 3. Okay. So that's the statement that I'm going to prove now. Okay. So I'm going to abbreviate that as 2 implies 3. Okay. That's what I mean. Okay. So here, this is our assumption. Now we have f which is closed. Okay, so it's 0. Sorry. So 2. If 2 implies, then okay. So maybe 1 is more easy to prove. So 2 implies 1. 2 implies 1. Okay. So let's change to 1. All right, so what we want to prove is that f satisfies this first condition, that if I take any closed curve inside the volume D, then I can take this line integral of closed curve is 0. So that means I have to start with any closed curve. Let C be an arbitrary closed curve, and actually that needs a little bit more mathematical rigorous. So let's find out more easier one. So before I prove the harder one, I want to prove the easy one. So sorry, I have to change 3 to 2. I think that's the easiest one. Sorry. Okay. Sorry. All right. So I want to assume that it admits a potential function and try to prove that it's a closed vector field. So we start from the fact that there is a function f that satisfies this equality. So that means our vector field is given by coordinate function fx, fy, fz. Okay. And then let's try to find out the curl of vector field. Again, curl of vector field can be written as the determinant of ijk del x, del y, del z of vector field fx Fy, Fz. And if you take the determinant here, we get first Fzy. So you have to take the partial derivative of y of Fz. So Fzy means that. And then minus Fyz. So that's the first coordinate. And the second coordinate is Fxz minus Fzx. And the last coordinate is Fyx minus Fxy. Okay. So here, now rigorously, these two are different. But we assume that our PQR, the coordinate functions, are differentiable, which means that it's C infinite. So which means that I can take many partial derivatives as I want and still get a continuous function. So therefore, the condition this function admits this f admits a potential function. F means that this f is also differentiable, which means that I can take a partial derivative many, many times and still get a continuous function. So since f is differentiable, which means that it's infinitely differentiable, so is f. And now, do you remember that we talked about the condition where the double partial derivative fails for some functions? There are some cases when we have switched the order of partial derivative for double partial derivative that the results are different. But it's same when you have a function whose second partial derivative is continuous function, because we assume that this vector field is infinitely differentiable, which means that if you take the second partial derivative, it's still continuous because you can take another partial derivative. That means you have to have a continuous function, and so does this function f. Okay, because this vector field came from the derivative f, so f must be infinitely many differentiable. So therefore, the second partial derivative, these are continuous. So therefore, all second partial derivatives of f are continuous. And what was the name for that theorem? Clairaut's theorem, maybe. But I'm not sure. So therefore, all coordinate functions are 0. Okay. 0. Okay. So that's the end of the proof. Okay. Seems obvious, but we need a little bit more argument to finish. Okay. So let's see. 네. So we're talking about the J component, okay? So you take the positive, negative parts here. So you have this is positive. Sorry, right? X. So the J component comes from xz positive. Right? You take these thing as positive and these thing as negative, positive and negative, right? So fxz is positive and fzx is negative. Okay. You remember how we compute the determinant of 3 by 3 matrix? Okay. This direction is positive direction. You find out all component that contains J. The only way you can make positive component is this way. So you multiply these two, which means actually not multiplying. You actually take an operation del z to fx. So you're taking del z to fx, z to fx. Okay. Okay, so we know that 3 implies 2. How about 3 implies 1? How about 3 implies 1? So we know that this vector field is given by a potential, it came from the potential function f. I tried to find out the line integral over closed field, closed curve. So let's assume that this is true. Then let's see, I'm trying to get a line integration over a curve C. It doesn't have to be a closed curve. Then how can you obtain the line integral? So let's try to take the integration here. So it says that if I have a parameterization of curve C by the small c, then by the definition that we already observed, it's a single integration from A to B of f, but I'm going to use this del f, so fx, fy, fz, inner product with what? C prime t dt, okay? But let's think about this case. So we have ct coordinate function as xt, yt, zt. So in fx, fy, fz, I actually plug in these ct points to find out the values here. So this is A to B of fx ct times, now this is a product between two vectors. So this is one vector, and c prime t, which is x prime, comma y prime, comma z prime, is another vector. So I multiply that with x prime t, and then add with fy, and then fz, z prime t dt. So that's the line integration from the formula of line integration that we deduced this fact. So what does it look like? What does this integrand look like?
Line integral for each axis.
But this is not a line integration. This is now scalar integration. Okay. But let's not look at the integration. Just look at the integrand here. What composite function? No, actually you cannot composite. Yes, C, right. So the derivative of composite function gives this integrand. So A to B of ddt of, well, at t, so maybe just ddt of fct is this integrand. Okay. Why? Because I know that f is x, y, z to f. Okay. And I know that c is from x, y, z. So let's take the composition of f and c and take the derivative that gives f by this is the chain rule for multivariable function. It's f prime times c prime. So what is f prime? It's a 3 by 1 1 by 3 matrix, right? So x prime fx, fy, fz, and what's c prime? It's 3 by 1 matrix. You take the x, y, z derivative by t. So this is x prime, y prime, and z prime. So you multiply these two matrices, you get this integrand, right? So we are talking about integrating the derivative of composite function, the one variable function, single variable function. So what's the result? fc b minus fca, right? So it means that if function admits a potential function f, the line integration only depends on the starting point and end point. Doesn't matter how you take the contour from this point to these 2 points. So what happens when you take the line integration over closed curve? What happens? In a closed curve, the starting point is equal to the end point. So you're subtracting the same point, same number, okay? Therefore, it's 0. So we proved that this condition is always true, okay? All right, so we have a triangle of 3 conditions. We proved 2 implications. So let's say here's a triangle. Easy one is 3 implies 2, and the other is 3 implies 1. Okay. 3 implies 1. How about the relation between 1 and 2? Two goes to 1. 2 goes to 1. 2 goes to 1. That's actually harder. That needs conditions. Okay. Oh, maybe not. Okay, so maybe 2 goes to 1 is easy one. Yeah. Maybe let's try 2 goes to 1. Okay. So assuming that we have a closed vector field having curl always 0, so what we want to prove is this equation. So do you see any relation between these 2 concepts? What kind of theorem that we need to apply? What theorem we need to apply? Stoke Theorem, yes. So if you know that Stoke Theorem is true for that kind of vector field, then since we know that the line integration is equals to the surface flux of the curl of vector field ds. But this is assumption that this is 0. So we are taking a flux of 0 vector field. So basically, this is 0. So if there is a surface, an oriented surface S such that the boundary of S is equals to C, then we can say this. So therefore, assuming that this curve is 0 implies that any curve C, the line integration of that curve C is equals to 0, right, by the Stoke's theorem. But let's think about whether we can whether we can find this oriented surface S for any type of curve C. So if you simply choose a curve like a circle, then yes, you can find out the surface S whose boundary is curve C. But you can make a curve in really complicated way, right? So maybe the curve looks like, so actually, it's called a knot theory, but so something like let's say you have a three-dimensional curve look like this. Can you imagine there's a surface whose boundary is this curve? It's very hard, right? So we need a theorem. It's a hard, deep mathematical theorem that tells you that in a three-dimensional space, you can always find a surface, oriented surface, whose boundary is any given closed curve. So for any given closed curve, you can always find an oriented surface whose boundary is that curve. So that's called a safer surface. So, I cannot draw. Maybe this maybe make it more complicated. So I cannot draw it here because I cannot imagine. But mathematically, there is a surface. You can always find a safer surface as an oriented surface whose boundary is the curve C. So you can argue this. Okay. Okay. All right, so we had these implications. So if you see this diagram, it's not commuting. Okay, so it's not circling. So in order to make it circle, so what if we can make this implication? Then now it's circling, right? So which means that 1 implies 3, and 3 implies 2, and 2 implies 1. So if you want to compare 1 and 2, so 2 directly implies 1. So 2 is a sufficient condition for 1. Okay? But also, if you follow these lines, assuming that this red implication is true, I can assume 1, and then passing through 3, I can conclude 2. So 1 is also sufficient condition for 2. So I can argue that 1 and 2 are necessary and sufficient condition each other. So we say that this 1 and 2 is equivalent condition. Okay? So basically, there's no difference assuming that F is conservative vector field or F is closed vector field, assuming that this red implication is true. So let's think about whether this is true, whether 1 actually implies 3. Okay? So question, does 1 imply 3 always true? So, right. Maybe I want to give a counterexample. Well, this is spoiler, but so we show that 3 always implies 1, all right? Let's think about the counterexamples. Okay. So okay, so maybe I should start from some special cases. So yes, the answer is yes if D is simply connected. So I'm going to introduce one more topological concept, which is called a simply connectedness. So the domain D is called simply connected if there's no kind of hole. Okay. So definition: a domain D. Actually, this is in any space. Although we assume that D is in R3, I can assume that D is in any n-dimensional space. Is called simply connected if any closed loop can continuously deform can into a point. Okay. So here's an example. Let's say I have a ball. Okay. Then, if I take any loop inside a ball, I can continuously, so this is a loop, so there is an orientation of the parameterization, but I can continuously shrink my loop into the point like this, so that eventually I can make the loop as just a one point, continuously make into a one point. So, but also think about ball with hole inside. Okay, so there is a vacuum inside. So it's not a ball, but it's just a kind of analogous here. So it's a ball. So it's an area, a volume between small ball and large ball. Also, let's talk about the loop in this volume. Okay. Since it's a three-dimensional thing, I can move away from the small ball and still make my loop into a point continuously. Okay. But let's think about this case. So we have a donut and I have a loop here. So okay, like a loop. I cannot shrink it to a point. I simply can't. Okay. Or maybe if I take sorry. So I'm sorry. So it's three-dimensional, right? So maybe I should make it into So maybe, does it make sense? You see what I'm drawing here? So it's a pineapple, okay? Basically pineapple shape, okay? And then thinking about the loop along the axis of pineapple, okay? Then you cannot shrink. So sorry for the last picture, the torus. Torus you can shrink because the inside is filled. I was thinking about the surface of the torus, but here we're talking about the three-dimensional volume, and these two are simply connected because I can shrink, but this is not simply connected because there is a closed loop that cannot be shrunk to a point continuously. I have to jump at some point to pass through this hollow axis. So this is not simply connected. Okay. So this is the case when three-dimensional, volume is three-dimensional. I can say similar for two-dimensional region, whether it's simply connected or not simply connected. So here's the example for two-dimensional. Let's say I have a filled region. This is simply connected. What if I have one point missing? Is it simply connected? It's not simply connected because if I have a loop around this one missing point, then I cannot shrink into one point continuously because I have to jump. How about a torus, like example I gave you? So this is the surface of a torus, it's not a filled torus. So then not only I have the loop that I can shrink in this direction, I have another direction of loop that I cannot shrink. So there are two totally different shaped loop that I cannot shrink into one point. So this is a topological side note that because of the shape, why we are talking about this effect as a topological fact is that in topology you can shrink or expand without changing the nature of the shape. So basically you can say that this is almost equal to just one point because you can shrink into one point. But here, so you can say that you cannot shrink into one point, but if you make it this boundary thinner and thinner, this is almost equal to the circle. Okay? And this one, you cannot shrink more. Okay? So you can make it thinner, but even if you make it thinner or thinner in this realm, the axis in here is hollow, so you cannot make it into this kind of figure here because you still have some hollow here. So this is that. So there's no way you can shrink more. So by looking at this simplified version, you can categorize your shape of the space in topological way, and people are working on, mathematicians has been worked on how you can categorize by looking at the shape of loops on these topological spaces. That's called the algebraic topology. So anyway, so these are simply connectedness, and let's assume that our domain D admits this simply connected. So assume D is simply connected. Then I want to prove that 1 implies 3. Okay. So how I'm going to prove is the following. I want to find out this potential function. Okay, that's my goal. So define f as follow. So pick, maybe confusing here. So first step, A step, is pick a point. So this is a fixed point inside of the domain D. And then for any x inside of D, or p inside of D, so this p is different from p0. So this is any p, any point p in D. Define fp, the value of function at p is given by a line integration from line integration over curve C. I'm going to define what curve C is yet later, of vector field where C is a curve from P0 to P. Okay, so that's a two-step to define the potential function. So I'm not saying that this is a potential function yet. I just defined my function. So now let's think about whether this definition makes sense. So when you define something in mathematics, you have to be the definition has to be flawless, because let's say if you define a function and I say function value is let's say something that I cannot determine exactly. So for example, what kind of thing is that? So sorry, I don't want to make it very rough example, but anyway, so I picked a point, so that's okay. But when I define something, so P is okay because I'm defining a function for this point P, but this value of function is defined on a choice of a curve, and I don't specify that choice. I just say that this is a curve, which means that it can be any curve. So generally, it makes problem. If you define something with random choice, you have to show that this random choice gives always the same answer in order to say that this is well defined. So well definedness of f. So how do you show that this definition is okay? Is you need to show this thing does not depend on the choice of C. Okay? So now let's go back to our basic definition. We have to use this assumption we haven't used yet. Okay? So it says that it's always the same. I mean, always zero. That means this assumption implies that if you have a point P0 and P here, and you pick a curve here, a closed curve, then if you go back and forth, always the line integral is 0. So let's say we have C1 curve this direction, and let's say this has minus C2 direction. Minus C2, so minus means it's the opposite direction. So assumption implies that So entire curve line integration, which is C1 minus C2. So this direction is minus C2. So P0 to P direction along the C2 curve is C2 plus C2 direction. So I'm just call it C2 here. Is 0. That means C1 integration and C2 integration. So it is always same. So it doesn't matter which path I choose. It only matters the starting and end points. So that's what assumption says. Okay? So assumption says if I pick any loop that contains P0 and P, and I split it into half, and if I pick this path or that path, it's always the same. So this actually equals to independent, and I mean the line integration. The line integral is independent to the choice of path. Okay? So I'm going to use that fact. All right. So here's our situation. Assume that I made a calculation of a line integration using C1. Okay? Then what can I say? I can say maybe, okay, so this is obvious, right? So it's not hard. C1 to C2. Yeah, so, okay, so anyway. So, yep.
Can we just, well, we actually show that FP is equal to, the definition of FP is reasonable because it fits the condition of the definition of function.
Mm-hmm.
So then we can just substitute the third, we can just substitute that the vector field is equal to some scalar value, the gradient of some scalar value function. So then maybe if we substitute that relation to the definition of FP,
Mm-hmm.
then we just get the total differential equation, the df.
So that's how we are going to prove that we are going to show what kind of f that is. So we cannot just say that there is some f. We have to show that what kind exactly that f is. So I try to define my f is. Okay, so I'm now in track. So I define my f concretely, and then actually I have to show that this is true, right? So there's another step that I should work on. So anyway, so by looking at this, now we know that this line integration of vector field doesn't depend on the choice of path, right? Obviously. So that finished the well-definedness of f, okay? So basically, this equation says that this does not depend on the choice of curve C, only depends on the starting point and end point, but starting point is fixed, so and it only depends on the endpoints, P. Okay, so that's that, and then try to find out, next step is this, our given f is equal to the gradient of f, okay? So let's try to think about the case here. We have a p here, okay, and we have p0. So it says it doesn't depend on the path. So I'm going to make a path like this from p0 to p, where at the end I'm taking a straight line parallel to x-axis. So it's p1 to p. So if p was x, y, z, then p1 is x minus delta x, y, z. Okay, so this is delta x. Okay, so let's assume this is my path. Okay, so what I'm trying to show is that if f is given by p, q, r, then p is equals to fx. Okay. Oh. So let's try to find out the ratio between ratio of the function f here. So fx is approximately delta x f of p minus p1, right? But then let's take delta x outside. And what is fp? That was the line integration from p0 to p. So let me call this a name. So this is C1 and this is C2. Okay. So if you want to find out fp, you have to take the path from C1 and C2, line integration. And then if you take the line integration to p1, you can take only C1 here. And what do you get? So there are common line integration of this vector field along C1. So you can cancel out these two. So only left with C2. But if you think about the line integration on C2, we don't have a change on y or z direction. So you only take account of p direction, x direction. So only p survives. So we have delta x. And on C2, I only change my x from x minus delta x to x of p dx. Okay. So if delta x is very small, then we can assume that this p is almost the same. And what do you get? P times delta x divided by delta x again. So you get canceling out. So we have left with p, and that was fx. So you can do the same thing with fy, fz. If you change the path here from like this path or that path. Okay. So where this simply connectedness came from. So so okay, I hope it's right. So okay, so let me think a little bit one more 1 minute. Think about the case here. So if it's not simply connected, then it contains the 0, 2, 2 does not imply 1, 2, 0, 2. So let's see, 1, 2, 3. So far we proved that 3 to 2, right? So okay, so 1, 2, 3. And so my concern is that in this proof, I never used the simply connectedness. So I'm considering that my assumption is not really necessary to prove this 1 to 3. Okay. So I'm trying to. So there is at least one of the implication uses the simply connectedness. So I was thinking that this is used in this implication, but it seems like it's not needed. So okay, that's good. Okay, so that's okay, right? Okay, so let's rewrite this here. 1, 2, 3, and 3 to 2. And 1, 3 are now equivalent. Now we prove both ways. So let's think about the case 1 and 2. Can I prove 1 implies 2 here? Can I prove 1 implies 2? Okay, sounds. Okay, so once we have that, okay, that's fine. Okay, that's fine. So nothing wrong. So every time I think about cases for two-dimensional vector field, now I feel it's not necessary. Only thing that I need here is that not simply connectedness on 3 to 1. But I think so when we prove that the 2 implies 1, we use that there is a surface whose boundary is the curve C, given curve C. Okay. So we use this theory on the mathematics. There's called the safer surface. That's we need simply connectedness there. Okay. So in order to have a safer surface, you need to assume that our domain is simply connected, because we kind of want to fill in this inside of curve. There's no inside, but somehow the volume that contains this curve has no hole in order to have a surface that fills this curve. So we need a simply connectedness here. I look up for the condition for the theory on the safer surface, but anyway. So in order to have this part, we need simply connectedness. Let me take back what I just wrote there. So we don't need connectedness, simply connectedness, to find out that 1, 2 is equivalent. So now, then we have a circling equation here. Let's try to, right, well, let's try to, let's try to make an analogous statement for two-dimensional vector field here. Maybe I should start from two-dimensional vector field in the first place. But anyway, so let's say I have vector field on two-dimensional, and my f is given by pq, and these are all differentiable. So for any closed curve in D, we have line integration always equals to 0. That's one condition. And the second one is that qx minus py equals to 0. The rotation is at 0. And the third one is that this vector field is given by the gradient of f for some f defined on D. Okay. So it's almost same, except that I changed my curl to rotation of f. Okay, and I'm assuming that my closed curve is in two-dimensional domain here. So I'm going to show that the first implies true fails if my domain is not simply connected. If D is not simply connected, then 2 does not imply 1. Okay. So there's a counterexample. Let me write there. Let's say my vector field is given by minus y over x squared plus y squared, x over y squared plus y squared. Okay. Let's talk about the rotation. So first take the partial derivative of x. So we have x squared plus y squared, x squared, y squared, minus x, 2x, and minus, minus the derivative of y of p here. So I have del del y of minus y x squared plus y squared. So we have, square, x squared, y squared, and let's say minus x squared plus y squared, and minus y of 2i. So we have minus here, so we're getting plus here. Oh, sorry, minus, or minus, so you have minus here. Okay. So if you add these two, what do you get? You have a 2x squares, subtract with this 2x squared, 2y squared, subtract with 2y squared, you get 0. So it's 0 rotational field, okay? Now, let's try to take the integration over the circle. So I'm going to define my domain of this vector field as one entire plane except one point, the origin, okay? So f is defined on R2 minus 0, 0. Okay? Because I cannot define function at 0, 0, but except there, I can always define my vector field. So C lies on this domain. So I take a line integration. So the line integration of that vector field, x squared, y, sorry, just to write it here, f ds is equals to, I'm going to parameterize ct as cosine t, sine t, and take t from 0 to 2 pi. So the p part is, so the denominator is always 1, it's minus sine t, and q part is cosine t, and take an inner product with c prime, which is minus sine t, and cosine t, dt. So sine squared plus cosine squared is 1, so it's 2 pi. So it's now 0, okay? So even though we have a vector field satisfying that rotation is 0, it does not always mean that the closed line integration over a closed curve is 0, because our domain is not simply connected. Our domain does not contain 0 here. Okay. Okay. So I don't think it's ever necessary to be really this rigorous in any application, because in most cases in the real life, you may not have a situation that function is not defined on some point. So you might work on a space, you might work on a function that defined on the field volume. So you don't have to worry about whether it's simply connected or not, because it's always simply connected. So if you see that anything happens among these three, then you can always use the other one as the same condition. So if you find out the formula satisfies that curl is always 0, then you can assume that there should be a potential function, or you can assume that even though you cannot find explicit potential function, you can always assume that this f is given as a gradient of function, and also you can assume that this line integration always depend only on the starting and end points. So this is a theory, and yeah, so let me finish our class by saying some properties of the Nebula here. properties of Nebula. So first of all, so it's important to know whether you can or you cannot apply the following operation on Nebula. So does this make sense? Makes sense because you have a vector as a gradient of function, scalar function. So here we have f as a scalar function and f, so this is three-dimensional function and this is three-dimensional vector field. So that makes sense. You have a curl of gradient and we know that this is always 0. Okay. Does this make sense? Yes, this makes sense because you're taking a vector and you take the inner product of Nebula, which means the gradient, the divergence of the gradient. So that's fx, x, fyy, fzz, and plus. And there's a name for this. Laplacian. Okay. If you have a function who says Laplacian is 0, it's called a harmonic function. And now next year you're going to be a sophomore. You will take linear algebra and probably engineering mathematics too. So you're going to learn about the Laplacian in the engineering mathematics too. And what kind of operation you can think of? So maybe I'm done with the scalar function. So what if I have this? Does it make sense first? Yes, because if you take the cross product, the curl, it's a vector field, and you take the divergence, what do you get? 0, yes. 0 scalar number, okay. Scalar function, sorry. Anything else? Well, I cannot think of any other combinations here. So maybe I can take divergence and divergence. Divergence and gradient. I'm sorry, gradient. Okay, that makes sense. So what's this? So you can just take PQR, PQYY and RZZ. So that's just simply taking second partial derivatives, right? Okay, so simple. So anyway, it's important to know whether you can or you cannot take these operations. It's interesting to say that. So let's suppose that so you have a Stoke theorem. It's S and curve C. Okay, so here's the orientation, and we know that the line integration is equals to the surface integral of curl of the surface over the surface. Can you apply divergence theorem to the curl of f on the right-hand side here? Because now it's, again, a vector field, right? You can relate that to another vector field and then try to use the divergence theorem to calculate this, right? Can you do that? Can you use the divergence theorem on the right side of this equation? What was the condition for divergence theorem? You should have a closed surface, right? Is this closed surface? No. So you can't. But what if you make your surface as closed surface? So suppose that I have another cap. So this whole thing is now surface S. Then I can use the divergence theorem on the right side, right? Right? But then this is equal to volume of divergence of curl and integration over the volume. But we know that this is 0. So we know that this is 0. But now what's going on the left-hand side? If I make my S as a closed surface, is there any boundary of that closed surface? Is there any boundary curve? You have a closed surface, like a ball, sphere. What's the boundary of a sphere? No, I mean boundary is the curve. Boundary of a surface should be curve, right? So boundary of this curve is 2 points. Boundary of surface is this line, this curve, right? So you have a two-dimensional object. The boundary is one-dimensional object. The boundary is zero-dimensional point. If you have two-dimensional surface, the boundary is one-dimensional curve. You have two-dimensional surface. Your boundary should be one-dimensional curve. But if your surface is closed, there's no boundary, right? That's definition. Closed means no boundary. If you have a closed curve, there's no boundary point, right? So even if you try to use the divergence theorem on the closed surface and try to use divergence theorem to calculate the Stoke theorem, your left-hand side is now pointless because there's no curve to take the integration on. There's no curve that you can take a line integration on. So there's no meaning to this. There's no meaning to combine the divergence theorem and Stoke's theorem.